All right, so today we are going to talk about quantification methods in MRI, and we'll introduce the susceptibility concept in MRI and susceptibility imaging. So the previous relevant contents will be those on spin density, the concept of T1 and T2, of course, and basic sequence, light gradient echo sequence and spin echo sequence. And also it was related to the field inhomogeneity we had to talk about. So today we are going to talk about how to quantify the spin density, T1 and T2, and we'll also discuss the susceptibility concept, phase imaging, and BOLD effects. Okay, so why do we need quantification? So up to now, most of the time when we are talking about T1, T2, all kinds of imaging contrast, we are talking about weighted imagings. So we are talking about T1 weighted imagings, T2 weighted, proton density weighted. So that means the signal is weighted by those quantities. But we do not know the exact number for those image contrast. So if we do a quantification, we want to know the exact number of the T1, the exact number of the T2 of a certain tissue. So we will need a quantification to quantify it. So doing quantification in MRI can give us very useful information about the tissues that's under investigation. So we can understand the tissue characteristics. If there is abnormality in the tissues, like if there is a tumor inside the brain tissues, then chances are we will probably witness change in those T1 or T2 characteristics, as well as other properties. So by comparing this different numbers of those parameters, we can provide a more better estimate of how the tissue has gone wrong, how the tumor has been developing. So quantification in MRI can provide us with very useful tissue characterization information. And also with different quantification methods, we can better understand the imaging contrast mechanisms. So we can understand how the T1 works under different scenarios, how the T1 and T2 works when we are choosing different imaging parameters. So we can talk about this later in the class. And also with certain quantifications, we can also help improve to optimize our scanning protocols or improve our imaging post-processing procedures. So for example, if we want to do a very perfusion weighted imaging, so we want to understand how the blood perfuse into the tissues. So before we can calculate this, we need to use our T1 map of the brain, so that we can accurately calculate the perfusion parameters. So there are many challenges when we are trying to do the quantifications. So one of the most routinely encountered challenge is that there will be other contrast mechanism at work. So there may be the signal is not purely weighted by the contrast mechanism we are interested in. For example, if we use a spin echo, we mainly want to get a T2 weighted image, and we want to use, for example, if we collect spin echo with different TE, then we can probably plot out the T2 decay, right? But if we are using a very short TR that is not long enough for the longitudinal magnetization to recover through the T1 effect, so that we will be introducing a certain level of T1 weighting into the signal. So that would lead to an error for the quantification of the T2. And also remember when we are talking about the artifacts. So when we are doing the diffusion weighting images, we have this T2 shrine full effect. So that means the T2 would also lead to an increase in the diffusion coefficient map that we calculated. So that so that would definitely increase the error of the estimate of the diffusion coefficient of the tissues if it also has a long T2. Okay. So there. And also there is a sequence challenge and different scan strategies that poses the challenge poses a lot of challenge. So how can we do the quantification with our efficient data acquisition? Right? If we can do a T1 map within 2 minutes, that would be great. But usually it's very difficult to do that, especially when we want to do a high resolution and, for example, a whole brain mapping of the T1. So we need to design the sequence so that it's as efficient as possible, but it can also give us a more accurate result as possible. And also there is the unknown baseline. So when we are doing a quantification, usually when we're talking about quantification, there are two kinds of quantification we are talking about. The first one is the absolute quantification. The absolute quantification is that we can come up with the absolute value of the parameter. The other is the relative quantification. We can only be able to estimate the relative values between the baseline and its change or the difference. So usually the absolute quantification is difficult to achieve. So when we are and the baseline of the signal is usually unknown. So sometimes we need to design a scan strategy so that we can come up with a signal that contains only baseline and the other signal that contains the baseline and a signal difference. So from the signal difference, we can come up with the relative change that is caused by the parameter changes. So that so most of the time we may be talking about a relative quantification. And also the noise is also a problem. When we are doing a quantification, we also need to do a good noise analysis so that to understand the potential error in the calculated results. Okay, so as we know, MRI is has multiple contrast mechanisms. So there are, I think we showed this before. So there are different intrinsic, for example, tissue properties that we can use as a contrast mechanism. Spin density, we can try to quantify it. For T1, T2, T2 star, and T1 row, we can also quantify them. Diffusion describes the thermal the thermal random motion of the water molecules. So diffusion can also be used to quantify it. The result is the diffusion coefficient describes how fast the water molecules can disperse from one within a given certain time. And also chemical shift, we can quantify how much of the chemical shift is, and what's the relative signal components for each different tissues or molecules that have a different chemical shift. And also susceptibility, we will talk about it later. And also temperature can also be quantified using MRI methods. So there is a temperature imaging or temperature mapping. So you use the image phase that we consider is also linearly proportional to the temperature. So this can be used to the temperature imaging can be used to monitor, for example, the ultrasound heating process that is used to treat certain type of tumors. And also the physiological parameters can be quantified. The blood flow, we can detect, we can quantify how fast the blood is flowing, the velocity of the blood flow. Perfusion, we can quantify how much blood is perfused into the brain tissue. Blood oxygenation is used to quantify how much, what's the percentage of the red blood cells that is oxygenated. And also there is also a tissue elasticity that we can also be used to quantify. For example, if we have there is a tumor inside a healthy tissue, normally the elasticity of the tumor is different from the normal tissue, and that we can also use quantify. And also this is some sequence-specific contrast mechanisms, and also other MRI quantifications that would include the B0 field inhomogeneity, as we've discussed before, B1 field, RF pulse field inhomogeneity, and also the water-fat ratio. This is people can use this method, this quantification method, to estimate how much fat and how much water, or just normal tissues for those obesity patients. So as we can see, there are lots of things that can be quantified using MRI. So today we are only going to mainly talk about the T1 and T2 quantification. So when we have simple spin echo, we know that its signal can be expressed in this simple way. It is weighted by this by the spin proton density. It's weighted by the T1 recovery, and it's also weighted by the T2 decay. So to obtain spin density weightings in the image, we can use a very short TE and very long TR to achieve a mainly weighted proton density weighted signal. And if we use a short TE and a short TR, we can obtain mainly the T1 weighted signal. And if we use a TE, long TE, which is approximately equal to T2, and we use a very long TR, so that we can have the signal mainly contains a T2 weighted signal. So there is also a latest development which is called the MR fingerprinting method. So this MR fingerprinting method can collect a series of images with varying parameters like the flip angle, TE, and TR, and then it uses complicated regression methods so that you can obtain arbitrary weighted signal out from the whole data set. So basically, when you do finish one fingerprinting scan, you can basically get a T1 map, a T2 map, a proton density map out of it at the same time. So this was a very latest development of the MR quantification method. I think it's being advertised throughout the society, but it looks good. Okay, so to quantify the T1 using a spin echo method, so we can use two different TRs and come up with two different signal intensities. So each signal intensity is weighted differently by the T1 term. So then we do a ratio between these two signal intensity, and then we can see that this ratio equals to the 1 minus E1 TR1, and the other is over the 1 minus E1 over TR2 of TR2. So if we introduce a total time constraint condition, if we say that we have T1, the sum of T1 and T2 as a fixed value, then we can come up with this plot. And with this plot, we can obtain a one-to-one relationship between the T1 and this ratio, this signal ratio. So in here, that means if we use this fixed total time constraint, that means if we use T total as 3 seconds, that means if we use TR1 as 2.75 seconds, then we will have TR2 only as 0.25 seconds. So from this plot, we can see that using this signal ratio method to estimate T1, we can see that it works best when when one of the TR is much longer than the other TR. And if if the difference between these two TRs is small, we can see that there can be a much large range that the T1 can be represented by the same ratio value within a certain error range. So that means using this signal ratio measure method and a fixed total time constraint, we can we'd better use a longer T1. We'd better use one of the TR1 much longer than the other, and we can get better one-to-one relationship between this ratio and the T1. So this is a relatively simple method. So if we use the same idea, the same signal ratio measurements to estimate the T2, and we collect the signal with the same TR, but two different TE. And the signal ratio now is the serum, and then if we do a signal ratio, we can come up with the T2 expression like this. It's only a TE2 minus the TE difference over the log of the ratio of the two signals. So this is relatively very simple. And also this is similar for T2 measurements if we use gradient echo and collect the gradient echo at two different TEs. So this signal ratio measurement, actually the what we call the two-point measurements, so that we collect two signal intensity with two different TR or T1, and then we use a known model, which is the exponential model, and we can estimate the T1 and T2. So this one, the advantage of this method is simple, and it's easy to obtain, and it's quick. It only requires collection of two data points. but it can be they can be more easily affected by noise, and error may also be quite large if we are not very careful about the setup of the experiment. So usually now people are using the multiple signal measurements instead of only collecting two signal points. So to estimate T1, we can have the we can also use the same similar signal ratio concept, but we collect the signal ratio with a multiple TR with the saturation recovery. So the so-called saturation recovery is that we do excitation of the signal, so that there is after with a 2 pi with a 90-degree 90-degree flip angle, so that we tip all the longitudinal magnetization to the transverse plane, so that the longitudinal magnetization will recover from zero towards equilibrium. So this is what we call the saturation recovery. So another way to do that is to do a multiple TI imaging with the inversion recovery. So inversion recovery is that we tip the do an inversion recovery using a pi pulse, and then we collect the signal the data recovery when during the signal recovery. So we can plot out the curve of that signal recovery, and then we can estimate the T1 that is associated with it. Also, we can also do this multiple TI with the saturation recovery, but it's not as good. The dynamic range of saturation recovery is much less than the inversion recovery, so the accuracy and robustness against noise is a little bit worse. And also there is another quick method that we can do to estimate the T1 value. So when we tip the magnetization, the equilibrium magnetization from the equilibrium state to the to the negative axis, then it will recover. So at some point it will go through a nulling point, to go through the 0 point. If we apply excitation pulse at that time point, we do not excite any signal. So that is the nulling time point TI. So if we can obtain that TI at the nulling time point for a certain tissue, we know that the T1 is directly proportional to that TI. So that's an easier method for the T1 quantification. Okay, so for T2 or T2 star quantification with these multiple signal measurements, first we can, of course, collect multiple TE imaging. So for each echo, we collect, for example, for each echo we collect one line of our K-space with that corresponding TE. So for multiple echoes, we can generate multiple images corresponding to different TEs, and then we use all these images to calculate the T2 or T2 star that's associated with the signal decay. So this is the this multiple TE method is the most widely used and very simple and easy to use for the quantifying the T2 or T2 star. And but we need to understand there is a different echo spacing for spin echo and gradient echo. For spin echo, the different echoes, they are separated by the refocusing RF pulse, right? So that means the echo spacing cannot be too small. While gradient echo, we can just use alternating radar gradients. So the efficiency of collecting multiple TE is very fast. So usually to do the T2 quantification, we will require much longer scan time than doing the T2 star mapping. And also when we are doing the T2 or T2 star quantification, we need to be aware of the two effects. The first one is the partial volume effect. So partial volume means that if in the voxel, in one single voxel, you have two different tissues with different T2 or T2 star, then if you're still using a single exponential model for the regression, then you will be come up with a answer that is do not faithfully reflect the true T2 or T2 star. So when you know there is a partial volume effect, then you will need to use a dual exponential model to do that. So you need to assume that there is two tissues with different partial volume ratios, and then use this weighted exponential dual exponential model to estimate the two T2 or two T2 star values of the two partial volume tissues. And also there is this water exchange effect. The water exchange means that actually the water, the free waters that is outside the cells, they will have a different T2 or T2 star than those waters within the cells. But there is also this water exchange between the water outside the cells and inside the cells through the cell membrane. So this water exchange can be very fast. If I remember correctly, it can be just a few hundred microseconds. So sometimes when we need to do a more accurate estimate of the T2 or T2 star, this effect would also need to be taken into account. So there are other different quantification MRI methods. So one of the also most widely used method is the loop locker. So the loop locker is that it's basically an immersion recovery pulse method. So it first it apply immersion recovery pulse, and then it use a series of small flip angle, usually it's EPI. So it collects a series of small flip angle EPI images that corresponding to different TIs. So it will give you a series of images that has a different, weighted by the different TI, and then it can in one single acquisition, if it's fast enough, we are not doing a very high resolution imaging, then with one single acquisition we can plot out the whole immersion recovery signal curve, and then we can just simply do a least square fitting to estimate the T1. The second one is the SSI, just like the gradient echo EPI. Just the gradient echo imaging with multiple flip angle. So we know that when we are in the steady state imaging, when we have a fixed TR, but we change the flip angle, we can obtain a signal change as a function of the flip angle like this. So for a certain TI, for a tissue with certain T1, then we know that we can actually estimate the T1 by collecting all these points and doing the regression for this signal curve. And also, there's this fingerprinting method that I just mentioned. It can give you almost many different parametric mapping and quantifications just with one single scan. But there is also some practical issues we must consider for doing the quantification MRI. So the first one is the time that needs to do the whole scan. So usually most of the quantification methods we will encounter in MRI, they are mostly done in 2D because if we do it in 3D, it will take much longer time. So for 2D, we can do alternating excitation or some sequence optimizations that we can give us some very efficient acquisition. But for 3D, usually it will take much longer time to achieve the same purpose. Another thing when related to the T1 weighting, T1 quantification is the slice profile. So when we excite a slice using a slice selection gradient, the slice profile is not ideally rectangular. So there is a slope down at the edge of the slice profile. So for those spins located at the edge of the slice profile, the actual flip angle is different as the nominate one that we are using. So for those, it will give you, if you use this method, it will give you a different curve. So when you are doing it, when you are collecting the signal from the whole slice, the whole slice actually a sum of all those signals. So that means the actual slice, the signal from the actual slice will be different from an ideal slice profile. So that's also something we need to understand and keep in mind when doing the T1 weighted, when doing the T1 quantification. And also there is the B1 inhomogeneity, the RF field. So this is especially a problem for the fast spin echo where we use multiple refocusing RF pulses. So for those multiple refocusing RF pulses, they usually are in pi pulses, 180 degree. So it's a large flip angle. So for the large flip angle, the block equation usually fails. So it will actually will give you relatively inhomogeneous B1 field in space. So that means some part of the object will experience a different flip angle, a refocusing flip angle than the other part of the object. So when that happens, it will lead to incomplete refocusing for those signals, and that would give you makes the signal decay even more faster. So that means if you use that signal, directly use that signal decay as your for your T2 estimate, then you can come up with a much shorter T2 because you will observe a signal that would decay much faster. But actually, part of this decay is due to the imperfect 180 degree pulse. And also the partial volume effect, as we mentioned before, if we know that there is two different type of tissues, sometimes like the gray matter and the blood, right? Or sometimes it's the normal water tissue, water-based tissue, and the fat-based tissues. If they, they are partial volumed, then we would be there will be some errors if we do not take into account the partial volume effects, and also the noise. All right, so the next part is on the susceptibility, chapter 25. So the definition of susceptibility, or sometimes we call them a magnetic susceptibility, chi, is used to describe the extent of a substance gets magnetized when this object is placed into an external magnetic field. So the definition is this: the chi is the magnetic permeability of the ratio of the magnetic permeability of this substance relative to vacuum, -1. So okay, so that means chi is defined relative to the vacuum itself in physics. But for MRI, usually it's difficult for us to encounter any vacuum situation. So in MRI, chi is defined relative to water. So the chi, the value of the susceptibility is usually of ppm, parts per million, or ppb, parts per billion. So it's a very small scale factor. So the definition of the magnetic permeability is that when the in here, if the object is inside external field, then we can then the permeability determines how much magnetic field can exist inside that object. While for the susceptibility determines that when an object is inside the external field, how much magnetization it can generate inside the object. So, and also whenever the magnetic field around the object would depend on many factors, like its shape, the susceptibility difference with its surroundings, and also the external field strength, and also the orientation of the object relative to the external field. So there are many factors that can affect the magnetic field around an object that has a different susceptibility with its surroundings. We can we can see about it later. So for the susceptibility properties, we have paramagnetic substance, or sometimes superparamagnetic substance. So for this kind of substance, we have susceptibility value, a positive susceptibility value. So that means this kind of substance, it will be attracted to the external field if it's near when it's put in that field. So it will also increase. That means this substance, it will generate magnetizations that lies along at the same direction as the external field. So by itself, it will just like generate acting like a small magnet itself that is has been aligned with the external field. So it will be attracted towards that external field. So the substance like this will include iron, magnesium, and aluminum. So we know that an iron is attractive to a magnet. So okay, so another kind of magnetization is the diamagnetism. So that means its susceptibility is smaller than is negative. So that means this kind of substance will be repulsed by the external field. But usually this kind of its susceptibility value would be very weak. So it will decrease the surrounding fields when it's put into external field. So the typical material will include calcium, water. Water itself is actually diamagnetic. and maybe sometimes it's a diamond. And there is the third one called ferromagnetism. So ferromagnetism, it also has a positive susceptibility, but its property is that it can retain the magnetization even after it's removed from the external field. So that means it itself can be more like permanently magnetized. So this kind of material will include iron, nickel, cobalt, gadolinium, and lots of alloys and oxides. So the examples of this kind of material would be the fridge magnet we see every day. And also there is this neodymium alloys. So this neodymium alloys is what used to make some very strong permanent magnets. So if you have ever break down a computer hard drive, you actually can find a very small magnet inside, just like this. So this the magnet in here is made with the neodymium. So the neodymium is very strong, can give you a very strong magnet. Usually it's like between 0.8 Tesla to 0.4 Tesla. So that means the one I'm holding in hand now, it has like around 1 Tesla magnetic fields within this area. So you guys can try to, that. So you guys can try to, break it open to, to feel how strong 1 Tesla can be. So remember that this the strength you need to break this open, to crack this open, is only from such a small magnet. So imagine that a full body 1 Tesla magnet, how strong that force you need to be to crack it open.
So this is 1 Tesla?
Around 1 Tesla. I'm not quite sure, but yes.
So here you say that gadolinium has the ferromagnetism property, right?
Yes, gadolinium itself.
So, as I know, it is used for one of the Venous contrast agents, right?
That's right. So when I say gadolinium, we only mean it's in its metal form. Oh. It's not in a complex form. Yeah, it's very interesting. If you put a stainless steel, right? Stainless steel is made of iron, but when you put a stainless steel inside the magnet, you do not feel it's being sucked. It's not. It has only very weak, magnetization in there. So that would depend on the form of that iron element is. Okay, so let's see how an object with different susceptibility behaves in the external field. So if we take a look at the sphere, in the case of sphere, the sphere would be very practical if we try to look at microbleedings inside the tissues. So when we have a sphere that has certain susceptibility, we place it inside an external field B naught, and then we can estimate the field changes inside and around this object. So if we have we know the absolute value of the susceptibility, the external field outside this sphere is expressed like this. So we can see that it's a function of the theta, which is the polar angle between the point of interest and the external field. So that means that the external field it generates will be different, will be spatially different, varying outside object as a function of this angle theta. And also, but for the inside, it will be basically it will be a fixed value. So, as we said before, usually we do not know the absolute value of the susceptibility. So most of the time we can only estimate the susceptibility difference of the object and its surroundings. So if we have a microbleed, we can only estimate its susceptibility difference relative to the tissues that surrounds it. Let's just put it there. Okay. Yeah, I got it. Thank you. So so then we can estimate the field distributions outside this sphere via this relative susceptibility difference. It's also very similar, and still the form is the same. It's still a function of this angle theta, and the signal difference. The field distribution inside the sphere is also a fixed value. So, and the next scenario is that for those vessels, most of the cases they are the wings. So we can model the wings using this infinite cylindrical body. So if we have cylinder that is placed inside an external field, this external field has the orientation of this cylinder has angle theta relative to the external field, and then for any point, observation points that has angle phi relative to the external field, then we can come up with this very complicated expression for the field distribution outside this cylinder, and also for the one that is inside the cylinder. Now we can see that, and if we use the relative susceptibility differences, we can come up with a relatively simplified version, and usually this would be much more realistic scenario. So from these two expression about the field distribution inside and outside this cylinder, we can see that it is also a function of the angle between the cylinder and the external field, and also it's a function for the one that's outside, for the external field distribution, we can see that it's also a function of the observation point. But for the for the field distribution inside the cylinder, it is only a function. Now it's a function of the orientation angle. So we can see that the field inside the cylinder now is also dependent on its own orientation. So a typical value of the water, the susceptibility of water relative to vacuum, is roughly -9 ppm. While the wing, the susceptibility difference from a wing between the wing and its surrounding tissue is usually only like 0.45 ppm. So the susceptibility difference of the wing is actually a very small value. So from this all these equations, we can take a look at how this field actually is distributing outside and inside the object. So for this is the sphere, and we have a B0 external field, and if we take a look at the profile along this line, which is parallel to the external field, we can see that the susceptibility inside inside the sphere is basically the same as the background as the surrounding external field. So there is no difference between the field inside the sphere and the external field. But immediately at the edge of the sphere, we can see there is a sudden change of the external field, and it decays as function of the distance. So this is what the field distribution of sphere looks like if we have the external field along this direction. So if we so this profile is along this direction. So if we take a look at the profile along this direction, that we'll observe a negative field distribution outside the sphere. So for these two, they are the different cases of the cylinder simulation. So we can see that inside the cylinder, it's if this cylinder is perpendicular to the external field, we can see that field inside the cylinder is at a fixed value of minus delta chi over 6. But so as we can see here, it's has a lower value relative to the background. But here we have the same value as the background. Okay, so if we have for different orientations, we can have a different external field distribution outside this cylinder. So along the parallel to the external field, we will have a positive phase, positive field distribution, and for the one that is perpendicular to the external field, we will have a negative field distribution. So this kind of effect, we also call them as the dipole effect. So the susceptibility effect in MRI can lead to several different behaviors or phenomena. So effect one is the dipole effect we just saw. It will create a different, according to its shape, whether it's more sphere-like or cylinder-like. It will create a different type of dipole effect around the object. So here is the real data we collected on the brain that has a very large microbleed in the tissues. So we can clearly see that this dipole effect surrounding this microbleeds, exactly like we have estimated in the as the sphere. And this is the simulation. This is also this is the simulation of this dipole effect, and this is the actual phantom data that we collected and render them in a 3D. So basically, the actual situation is very well predicted by the simulation. And here is the cylinders. We have a straw phantom that has filled with different susceptibility substance. So it will give you different susceptibility strength inside straws. So we can see that clearly see that there is different levels of strength of dipole effect due to their different susceptibility. So we are also seeing here, this is the 5 straws in here. So this is also very well predicted by these cylinder models. Okay, so the second effect is that it can reduce the T2 star by increasing the local field inhomogeneity. This was discussed. We discussed this in the chapter of field inhomogeneity. So if this is a voxel, then it contains small source of susceptibility. Then we can observe it will create a dipole effect around it. Then if we are looking at the spins at these different locations, it will after it's being excited, we can observe increased dephase process, just like this. So this is basically increased T2 star decay process. So the effect is that it will reduce the T2 star value and give you a much faster signal decay. And also the third effect that we usually observe in imaging is the signal dropouts or distortions at the boundaries or with large susceptibility differences. So this is what we usually observe in gradient echo-based sequences. We have, because there's a lot of air in the sinus, and the air has a very very large susceptibility difference relative to the brain tissues. So there is a very strong dipole effect around these boundaries, and this dipole effect will lead to a very significant T2 star decay at these local regions. So we can observe a signal dropout, so like the edge of the brain is being eaten out due to the enhanced T2 star decay. And here are the two images we saw before. For this, because the susceptibility, it creates the dipole effect creates field variations outside an object, right? So this field variation by themselves, they are very strong background gradients. So for those background gradients, it can either create a very strong signal blackout for the gradient echo sequences, or it can create a signal signal distortion and signal shift in the spin echo based sequences. And also the fourth effect is actually a very useful effect. It's called the BOLD effect, the blood oxygenation level dependent effect. So this is widely used in the fMRI. So when the brain is at rest, we have baseline blood flow, baseline oxygen saturation inside the veins. But when we are being activated, when the brain region is activated, there will be an increase of local blood flow. So an increased local blood flow would bring more oxygenated blood to the vessels, to the veins. So that means it will change the susceptibility property of the venous blood here, and then it will lead to a T2 star change in the image signal. And this is a very typical activation pattern if we are using a flashing checkerboard and a black background. So we can observe a very clear signal change as this stimulation pattern changes. So for the susceptibility and the BOLD effect, we know that venous blood susceptibility is related to the oxygen saturation, hematocrit, and the blood flow. So for those hemoglobin, which is oxygenated, it will have diamagnetic properties. So as we said before, the diamagnetic substance usually has a very weak susceptibility value. But for those de-oxyhemoglobin, it will be paramagnetic. So it will have a relatively much stronger susceptibility effect relative to the tissues. So that means the oxygen saturation, which is the percentage of the hemoglobin being oxygenated, will affect is the basis for the BOLD effect. So most of the time we need to estimate the oxygen saturation level. So as it is a function of the oxygen saturation and hematocrit, we can see that the susceptibility of the blood is a function of the hematocrit and oxygen saturation, and of course the susceptibility of oxygenated blood, oxyhemoglobin and the de-oxyhemoglobin. So most of the time when we estimate susceptibility of the blood relative to the surrounding tissues, this is the empirical equation we can use. So it's clearly a simple and linear relation to the hematocrit and the oxygen saturation level. So that means if we can quantify the susceptibility of the blood, and if we know the hematocrit, then we can calculate the oxygen saturation. We can determine how much oxygen is in your blood. And also, oxygen saturation level is, of course, function of blood flow. So if you have higher blood flow, but your oxygen extraction, the brain is still using the same level of oxygen, and then you will, of course, have more oxygen left in the venous outcome. So that means the oxygen saturation is dependent on the blood flow. So this is also the relation that we can use to estimate oxygen saturation level in terms of the blood flow change. Okay, so last part, let's take a look at how we can measure this local magnetic field variations. So usually the best way to do this is to do the phase imaging. So when we do the phase imaging, the image phase is actually it's very simple, as we have already seen this in the first few chapters. So the phase in the image is actually the directly is related to the field variations and echo time we use. And of course, most of the time there is a baseline phase that we may not know. So this is the phase image we collected for I think it's a sphere. For a sphere that has strong susceptibility effect. So we can see that with a shorter T1, we can see the phase image like this. With a longer T1, we can see the phase effect is even more has extended, is more extended spatially. But we should always remember that susceptibility is only one of the properties that can affect the image phase. So other factors that can affect the image phase will include the chemical shift, right? Because there is directly a number frequency difference between the, for example, water and fat. And also there is a motion. We'll be talking about this in next chapter 23. So motion will also lead to a phase change in the image. And field inhomogeneity, as we saw before, is directly affecting this term. So it will definitely lead to a phase change in the image. RF pulse itself can also lead to a phase change. If we have, and also gradients and background gradients, eddy currents, they can also lead to a phase change. So when we see, when we are talking about phase image, we need to be able to distinguish the phase effect that is from the susceptibility difference from all these factors. So one of the simple way to do that is that only susceptibility variations will lead to the dipole effect like this. For others, they won't have any of the dipole effect. And also, when we're talking about phase imaging, the phase information is usually best revealed by doing a high-resolution gradient echo sequence, because we can see that it's directly proportional to T, and it's more like a gradient echo imaging. So, we also need to see that we can see that here there are lots of wrapping of the phase. It goes from the highest value or very bright value and to suddenly the negative value. So that's because the MRI image, it only stores the phase in a 2 pi range. So once that phase has developed over higher than a 2 pi range, and this phase would wrap around to the other to the negative. So that means we need to, if we want to estimate the field distribution from the phase, we need to first unwrap the phase. So there are lots of algorithms and efforts put into the unwrapping this phase image so that we can better estimate field variation that's associated with this susceptibility difference. So there are also other methods to measure the local field, magnetic field variations. There are magnitude imaging methods that can measure the field variations. If we remember that steady state free precession signal profile, right? We remember that once every 2 pi of this phase offset, we will be observing a signal stop band. So this would, is on a periodic basis. So we can see that sometimes we can see we know that this line along this black line, they will all have the same frequency. So in here we can see that the global field variation is have this shape along this So this is one way to estimate the local magnetic field variations using the SSFP. Another is, of course, to do a T2 star mapping. Right? When you have T2 star map, for those regions that has a shorter T2 star, that means it will have a higher variations in the local magnetic field. And also you can do a T2 mapping for the local field variations. And for phase imaging, the most widely used method is, of course, the gradient echo sequence, because it's the phase is directly proportional to the TE. Another less used method is the shift echo, spin echo. So if we have for spin echo, we have the 90-degree excitation pulse, and then we have 180-degree refocusing pulse, and then the echo would appear at the time that is the same as the interval between the echo and the 180-degree RF pulse center is the same as the excitation and refocusing pulse, right? So if we shift the spin echo, then that means shift the acquisition window for the spin echo. That means that there will be an extra phase development that is not refocused by the refocusing pulse. So that means in the echo it collected, there will be an extra term of phase collected. So it will more like become a little bit like a gradient echo sequence. So this is a relatively less used method for phase imaging. Okay, so these are the homework for this course, and the next section will be on chapter 23. Okay. All right. Is there any questions?
Yeah. If we have some arbitrary shaped object, then how will we quantify the change in?
I'm sorry?
If we have some arbitrary shaped object other than sphere or cylinder, then how can we map the change in magnetic field?
Well, actually, that so these equations that we come up is actually derived from the Green's function. So the Green's function is a general function that is not dependent on the shape of the objects. So this is just a direct it's just a direct computation using the if you know the shape, if you don't know the shape, if you know the susceptibility distribution map, and then you just directly multiply it with the Green's function, and you can come up with the distribution, its estimated distribution of the field. So this is actually this is basically the idea for the swim. So we need to calculate the inverse function for the Green's function. So so the Green's function is not dependent on any specific object itself.